LTQ 7.2 exponential graph. Sorry, my other video got cut off. So, we're going to start now. All right, so LTQ will do 7 and 3, and then maybe 4. We'll see. All right, exponential graphs. The graph on the right follows the formula y equals a. That's initial, right? B, multiplier, to the x. So what is the value of a? Okay. So, you can see this point here is when initial value is when your x value here is 0. And these appear to not be good. Let's take those off. If this is 0, 1, and this looks like, and that's 1, 3, and that's 10, this looks like this is scaled by 3. So I don't like the 5 and 10. They don't match. All right, so here we are. So a is 1. Our initial value is 1. That is when this x is 0. All right, so I can kind of get my formula going here. Y equals 1 times b to the x. We know that the a value is 1. And so what's the value of b? Well, let's just grab another point. Let's grab this point. And so remember, this is a point xy. So I can put 3 here, 1 here, and because that's a, right? That's your a value. And this x value of 1 right here. So it's x right here, and this y right here. So this lets me know that b is 3. So b is 3. So if you were to write this function, it didn't ask us to, but if you were, it would be y equals 3 to the x. All right? Or y equals 1 times 3 to the x. All right. From our notes, which function grows the fastest? So we're looking at all the bases. Those are all greater than 1. Those all have a base greater than 1, so they're all growth. So that's good. So as we look at this right now, this appears to be the biggest. But we have to look at this one. And remember, e to the first power. So e is this 2.71828, etc. value. So this one here is actually the biggest because it has the biggest base. So that was A. All right, so wow, that's 7.2, pretty easy. Okay, so now let's go into 7.3. We write each equation in logarithmic form, 1 point each. Okay, so we're just going to, the base, this is the base here, and that's going to be the base of your logarithm. And remember, the log equals exponent. So that's your exponent. So that's going to be log equals exponent. All right? So you got the base is the base, and that's the subscript here. And so the 1/2 goes to the other side, and then the 8 is right here. So this is log 64a equals 1/2. Okay? Log base 10. It's got to equal the exponent, so there's only place for 100 to go is right here. And remember, this log 10 is the common. And we just write log. So you could just write this as log 100 equals 2, or log base 10 of 100 equals 2. Okay, so let's go the other way and exponentiate this. So you just start at the base. 5 log equals exponent squared equals 25. So base 5 squared equals 25, which makes sense because 5 squared is 25. So you start at the base, raise it to the exponent, log equals exponent equals 25. Okay? So this really confuses people when they have to compute, because now we just have this expression. If you need to always put an x there, you can. Because this is, and that's not what it equals, obviously, but you're asking yourself 2 to what power equals 32? 2 to what power equals 32? And that would be 2 to the 5th equals 32. So that is 5. All right. And then the same thing on the next one. This is 10 You could put an x here. So 10 to the x equals 52. Well, I don't know this. This, 10 to the first, 10 to the second is 100. Cubed is 1,000. Fourth, 10,000. This is what I don't know. So this would be a calculator problem, and your calculator is built to do logs in base 10. That's log. So you can just punch this in, log 52. And it will tell you 1.716. And what that means is 10 to the 1.716. The logarithm is solving 10 to what power is 52? I mean, before logarithms, you'd be like, I don't know. I have no way of knowing that. But now we do. So just check it out. 10 to the 1.716. Well, 10 to the 1.716. You see you get that 52 right there. So logarithms are really cool in the way that they can allow us to write any number as a power of another. All right? And then inverse here. So, of course, we switch x and y. We know that from the previous section. So I'm going to switch x with y. I'm going to switch y with x and x with y. All right? And then I'm going to write it in log form. Okay, so log, base is base. Log always equals exponent. And then that would be x. And there you go. So the inverse here, and this would be as if this were f of x equals 5x. The inverse here would be log base 5 of x. All right, so that is 7.3. So let's do 7.4, properties of logarithms. Evaluate the following. My hint would be to put an x on this and circle around the problem. 3 to the x equals 27. And x is then equal to 3. You can also do, 3x equals 3 cubed. And if base equals base, then x has to equal 3. Okay? Set it equal to x. 2 to the what power is 1 over 16. 2 to the x is 1 over 16. Okay, well 2 to the x is 1 over 2 times 2 times 2 times 2 is 4. So, 2 times 2 times 2 times 2 is 16. Make it uncomfortable. And there you go. X is equal to -4. All right? I'm going to use my properties here, that the log base 3 of 3 squared. Oh, sorry, 3 cubed. 3 cubed. Okay, so 27 is 3 cubed. All right, so if I can get these bases to match right here, then that will all just negate, right? So log base 3 of 3, perfect. That all negates. Those are inverse operations. And then I just have 2 times 3, which is 6. All right, those are really fun. Okay, the next one deals with properties. Let's see. So log base 3 of 3. So if you can get these right together here, they just negate, and this drops down. That's just 7. That's that property we talked about in class. Easy, easy. We like those problems. And then same thing here. That's a 5 to log of. Those are inverse operations. They cancel, and 12 just pops down. They cancel. It's this 12 just drops out of the air. Log base 10. So this is log base 10 of 10. Okay, so those just knock each other out to 1. And then let's think about log base 9 of 1. What is log base 9, 1? Well, let's set it equal to x. Like, you can always set something you don't know equal to x. If I circle around the problem, 9 to the x equals 1. Okay, so when I raise something to a power and get 1, that power has to be 0. Okay? The only way to get anything to equal 1 with an exponential equation is the exponent has to be 0. So this is actually equal to 0. So this is just 1. Okay? In expanding logarithms, when you have the same base and you have this tucked behind the logarithm in division, those will become the log attached to each of them, and they'll be subtracted. Okay, so I'm not truly done there. This one's done. This I can put in my answer key, because that's just log base 3 and y. You want just one thing behind, and you know you're done. So now I got to deal with this. So these are being multiplied. So I can split those with addition. Log base 3 of 2, that's done. Plus log base 3 of x squared. Again, log base 3 of y. Okay. So that piece is done, because you just have base 3 and one item behind. So the last thing I have to do is deal with this, and this exponent from our properties goes down in front. So the final answer here is log base 3, one thing, perfect. 2 comes in front, that square comes in front. Log base 3 of x, that's what's going to fit right here. Okay, minus log base 3 of y. All right. So can I put the rest of it here? Log minus log base 3 of y. And this is this problem right here. Okay. So yeah, so if you were to, put this back together, that would be 2 times x squared over y, which is what you see right there. And so you're going to expand and condense. To condense, we're going to do exactly what I just said. So these are all log base 3, great. And we want everything behind the logarithm. So 7 is a positive, so it's going to go up top. The coefficient becomes an exponent. That's a positive term, so that's also in the numerator. This is a negative term, so it's in the denominator. And this is a negative term, so that 5 is in the denominator. So that's how this would condense. Okay, so 7 is up, x cubed is up, minusing, that's down, and minusing, I'll put it in front. All right, last one here. Rewrite using the change of base formula. Do not evaluate. So your calculators can't really handle this, so we change the base. This is the base here, and we think basement. So we just write these as log base 10, and you just put the 15 in the numerator and the 12 in the denominator, both base 10. Or later on, you'll show that you could use the natural log of 15 over natural log of 12. But we won't do that yet. We'll just stick to log of 15 over log of 12, and that's base 10. So your calculator doesn't know how to do log base 12 or 15. There's nowhere to do that, but it can do log 15 divided by log 12. There you go. Didn't ask us to evaluate, so we'll leave it at that. All right, I'm going to stop the video here, and I'll pick up on the next 2 LTQs. Bye, guys.